Dear colleagues, I would like to welcome everyone at the 9th edition of the Aerospace conference. I'm really grateful that we can have all of you here in this room. As well as I would like to greet our online participants, and I would like to thank our media partners for the online streaming of this event, which is available on the YouTube right now. My great pleasure to greet Gergely Zarand, the Vice Rector of the Budapest University of Technology and Economics, and I would like to give the floor to him.
Thank you very much, Laci, and thank you very much for the invitation that I can be here. It's a great pleasure to welcome everyone, also present and also online, at this conference, the Aerospace 26 conference. As Laci said, this is the 9th conference of BME on space science, research education, and also education on the top of that. We all know that space is becoming more and more important, and I don't want to say, and I don't have to say too much about that for this community, but maybe it's good to recall that the whole thing started maybe in 57 by Sputnik 1, orbiting around the Earth, and then 97, that's actually my date of birth, when Neil Armstrong stepped on the surface of the moon. And then in the 70s, the GPS systems have been developed. There's also an interesting twist on that, which is interesting for Hungarians. This is the ideas or nightmares of Edward Teller about Star Wars. That was also in that period in the 70s and 80s. Then 2002 was Elon Musk created SpaceX, if I recall correctly. And since then, there's been a huge development, and by now, more than 10,000 satellites are orbiting around the Earth. Actually, more than that, but the 10,000s are active from the satellites. So it's a huge development, and space technology is of clear importance. BME has, from the beginning, or from the start, has been committed to participate in these efforts. It's very fortunate that we do have the potential for that. Space technology requires a lot of backgrounds, including materials science, communication, information theory, today AI, quantum communication, quantum technology, and I could go on with this list. And BME is very glad that we are actually very strong in all these fields. So this is why we can participate and can participate actively in this research. And maybe I could go back to the first real step of BME. This was the launching of the MESSAT satellite. Since then, six satellites orbit around the Earth. I don't know if some of them dropped down, but hopefully not. I'm sure that some of them are inactive by now, but we still have active satellites, nano and pico satellites, as Laci likes to put it. These are very tiny satellites which communicate with us here in BME, and we are very proud of this achievement of our researchers and our students to have that. Also, BME participated in many developments earlier on, and even today, so we are a part of major international missions, space missions. Maybe I would mention only the HERA mission, where BME engineers participate in the development and improvement of the optical system of spacecrafts. But there are many of such developments at BME. So we're very proud of that. And of course, BME also was very initiative and started launch programs in education. We launched the first space engineering program, MSc program at BME 4 years ago. So the first cohort is already out. We also participate in the Unispace program of Hungary. This includes 22 universities by now. BME is one of the program leaders in this effort, which is a postgraduate program to really deepen your your knowledge, the knowledge of engineers in space science and space technology. And what is also very nice, Hungary launched an astronaut program, HUNOR, and Tibor Kapu, the Hungarian astronaut participating in that, is standing next to me. So we were very glad to launch a program together with Tibor called Universe Zoom, which was a student for students to make space science quite interesting for students and attract them towards this segment of science and technology. So within this effort, why Tibor stayed abroad on the International Space Station, we performed some experiments, and a few thousand pupils could also do the same experiments on Earth and learn what's the difference between space and Earth, or gravitation, or being well, in this state of free fall. So this is we are also committed to that, and we are developing our programs. Our friends and colleagues are really developing these programs with a great effort. So clearly, space holds a future, and this is why all you are here, and why this conference managed to grow from a local conference to an international conference of more than 200 participants from more than 20 countries, and became a huge event. And this is a place to actually thank you all, especially the organizers, Lotzi Bocciardi and Carmen. I have a list that actually Lotzi gave me, so I need to go through that list, because of course I need to thank our partners, and forgive me if I omit someone, this list, because it's long. So first of all, I would like to thank BME's Cosmos College for Advanced Studies, the Hungarian, you're allowed to applaud if you're, Hungarian Astronautical Society, Hungarian Association for Innovation, the Space Generation Advisory Council, and the Women in Aerospace Europe community. So space, yes. So thank you all, and I would close with that, but this thanks to the organizer and you participants. I wish you a very pleasant conference. Enjoy the talks, enjoy the networking, and have a fruitful conference here in Budapest. Thank you very much.
Thank you very much, Vice Rector, for your greetings and for your words. This conference is dedicated for science, technology, and education of space. And this is why we are really grateful that we have someone here in front of you who conducted several scientific experiments on board of the ISS. With this, I would like to give the floor to Tibor Kapu, our Hungarian astronaut.
Thank you. Hello, everyone. My name is Tibor Kapu. Thank you for having me. If you have not too much knowledge about who I am, I have been to space last summer for 20 days, a little bit more than 20. It's actually 20 days and 3 hours. And during that mission, I spent 18 days on the International Space Station. That was due to, or thanks to, a space program which is called HUNOR, as Vice Rector said. We have a space program in Hungary. It started in 2021, basically, with some of the astronaut candidates or applicants. And then, at the end of the whole program, it became the 4 of us candidates. I was selected 2 years ago, actually. The anniversary will be in a few days only. We moved to Houston after that, and last summer I had the privilege to fly with 3 of my, not even colleagues, but friends at this time. And I will tell a little bit about them, because my commander was Peggy Whitson. She's from the US, she's from Iowa. She is the most experienced US astronaut, female or male, and also the most experienced female astronaut around the world. She spent almost 700 days in space, and that's why we were extremely lucky to have her as our boss, as our commander, during the preparation phase, the training phase, and also during the mission, because there's no one else who could give us more experience and more wisdom and knowledge than her. And then we had a pilot, Shubhanshu Shukla. He's from India, he's from the Air Force, and we also had a mission specialist like myself, and the other guy was the Polish guy Sławomir Uznański-Wiśniewski, his call sign was Swav. The reason I'm mentioning this to you because this is, 4 people, 4 nations. So clearly this is an international mission. This was called AX4 because it was coordinated by a private company called Axiom Space. And within that international mission, we conducted 60 experiments on board the ISS in 18 days. Out of that 60, I had 25. If you divide 60 by 4, you will have the results of 15. So obviously I did much more than the other guys, but that's thanks to my colleagues in Hunor back at home. We utilized every single second that I spent up there. But the main importance in this is that we also conduct each other's research. So I always talk about the 25 Hungarian research that we did, but there are also many more that I conducted for them, and they conducted some for us, meaning that when you have an international crew, you also contribute to international science. I have been doing Polish experiments and I have been doing US experiments as well. Meaning that when you are part of this kind of crew, this kind of community, you have one of the best abilities, the best chances to contribute to science internationally. And that's what I'm actually very proud of, that with Hunor, with this space program, we started to build an international basis or community for our advancements later on, especially in the scientific field. That was one of my main messages, and the other one is that I also finished my master's here. I just recently started my PhD. I was not the most or the best student this semester. I will try to do more. We will see how it goes. But basically, I finished here as a master's engineer in mechanical engineering, and I was very proud of that. The reason I'm telling this to you is that out of that 25 experiments, many engineers, many scientists, many researchers who prepared those sciences are from the same university, same walls, same background like myself. I could tell you many examples for that. Many young engineers came out from these walls and conducted space research, space science, also within the Hunor program. So I believe that these walls spark curiosity, spark inspiration, and that's why I'm actually very proud to be here. So I also wish a very fruitful conference for you, and thank you very much.
Thank you very much, Tibor. And as an associate professor here at BME, I wish you really good weeks for this semester and for the remaining time of your PhD studies here. As you could hear from our vice rector, we have many partners for this year's conference. And on behalf of the organizing committee, I'm really grateful to all of them to contributing to our scientific missions as well as to contributing to the program. But we have a really long-lasting partnership with the Hungarian Astronautical Society, or MANT in Hungarian. And this is why I would like to ask the president of MANT, Kálmán Kovács, to give his welcome speech as well.
Thank you. So, dear Vice Rector, dear research astronaut, dear ladies and gentlemen, please allow me to begin with a personal thought. When the idea of this conference series first came to my mind in 2015, Hungarian space research was going through a very successful period. So that was the time when, after many years of preparation, Hungary finally became a full member of the European Space Agency, ESA. And at the same time, the small satellite, as was mentioned, designed and built at our university, Masat-1, the first Hungarian satellite, had already been operating flawlessly for 2 years and continuously sending images from Earth, of Earth back to us for our luck. And now I feel the same excitement again. Alongside many other successful projects, the mission of our research astronaut, Tibor Kapu, is another outstanding event that draws the attention to the whole country to space research. This attention gives our space community a great opportunity to research how important the space technology could be for Hungary and how important it is for the future of our nation and how its possibilities can benefit every area of life. Once again, the Aerospace conference can play an important role in this effort. On the one hand, it is an excellent professional forum when we can share our scientific results with each other, but on the other hand, it is also a great opportunity for the wider public to see that successful and innovative work is being carried out in many research institutes and industrial environments here in Hungary. Since the very beginning, the Hungarian Astronautical Society has published the conference proceeding as well as the volume of selected papers. We would like to encourage all participants, speakers, to submit articles based on their presentation for this publication. Finally, as a co-organizer of Aerospace 2026, please allow me to wish all participants inspiring conference, excellent presentations, and useful discussions in the breaks. Thank you for your attention.
Thank you for all of you, and with that I declare the Aerospace 2026 conference to be open. I kindly ask you to take your seats, and I will have some housekeeping information. So we are organizing this conference in a hybrid form. Today we will have an in-person day, and tomorrow we will have the whole day as an online day. We already sent out the Teams link for tomorrow's event. This afternoon we will start with a keynote presentation, and it will be followed by the poster flash talks. The poster flash talks will be held in this room. We have the PowerPoint presentation ready for the presenters. And after the poster flash talks, we will have the coffee break with the poster session, and it will be followed by a plenary session in this afternoon. And by the end of the day, we will have an official side event organized by the Women in Aerospace Europe. This side event will be held in Hungary and in a different room at the ground floor. Having said that, I would like to introduce our keynote speaker, Dr. Tibor Bálint, who graduated here from the Budapest University of Technology and Economics a long time ago. He had an incredible life career, spending some years in the UK, in Canada, and as well as in the US. He retired from the NASA Jet Propulsion Laboratory, but he used to work at the NASA headquarters as well. He's member of the International Academy of Astronautics. He's member of several committees of the International Astronautical Federation, and recently he has been awarded with the IAF Distinguished Service Award. So we are really happy that we can have you here. And if you are participating in the Aerospace conference series since the beginning, he was one of our keynote presenters maybe in 2015 when we started, or 2016. So 1 year after we started this event. He is member of our international program committee since the beginning. So we are really happy that we can have you here. And just switching to your presentations, and here is the mic for you.
Great. Well, thank you very much for inviting me to present here at the conference. It's nice to be back after 10 years. Let's see if it's working or not. No signal. Oh yeah, success. Oh, I'm back. Great. So nice to be back. Thank you very much for inviting me. I will talk about human-centered design and how it can benefit the space sector. While the conference is focusing on research and technology and education, this is something totally different, but you will see somehow it's related to the big picture. So I will talk about a couple of things. First, about my journey, how I got there, how I get here where I am. A little preamble about human-centered design. Then talk about 3 different things. One of them is boundary objects and why I think it's very important as a designer. The second part will be about the design environment at JPL, called the Innovation Foundry, how it works, and where design can benefit the workflow over there. And the third part will be a little bit about human-centered design for human space exploration, where opportunities can arise, where designers can contribute meaningfully. So about my background, let's see if it works or not. Oh yeah, here. So after graduating from university here, I went to England. I got another degree in chemical engineering, another master's, and from there I went to Canada, and I worked there for 10 years in the nuclear industry. From there I went back to England. I got a PhD in biomechanical engineering, and from there I went to the International Space University because I wanted to get some space experience. And from there I did my internship at the Jet Propulsion Laboratory over there, and I was there for 23 years, but not continuously, because from there I went to NASA headquarters for 4 years when I worked for the Space Technology Mission Director as a program executive for a space program, space technology program. And after that I took a couple of years off and went back to London, to the Royal College of Art, and got a PhD in human-centered design. And from there I returned to England. From England I returned to Canada, to California, to Pasadena, to JPL as the principal human-centered designer. So I've had exposure to mission design, space technology, a little bit of science through the proposal work I was doing with other scientists, and a little bit of human-centered design as well. So human-centered design. If you look at the space industry, it's typically built on technology, science, and management. And design was initially not part of this paradigm. But human-centered design is an emerging discipline which can benefit the space sector, in my opinion. So it can broaden the paradigm. It doesn't replace anything, but adding design to the current workflow can give us more opportunities and more options. So design is not to make something pretty or something beautiful. Instead, we have to demonstrate that by adding design, it can have a demonstrable, meaningful impact on the missions. For example, how can we reduce risk by introducing design? How can we reduce cost? How can we improve on the schedule? So human-centered design can play an important role in different parts of the mission formulation, mission implementation, mission operations, so throughout the whole process, and not only for human exploration missions, because human-centered design, but also for science missions as well. So let's say a few words about the kind of mission development. So it starts from an ideation when I have a great idea, let's do a mission about something. And then eventually go through the development phase for designing, building, testing, and operating the space mission. And there is a scale called the Technology Readiness Level scale. TRL 1 means that I have an idea, like a paper or napkin idea, and TRL 9 means that we are actually flying this instrument in space. So we are going through this development process, and then we measure the progress of the technology development through the scale from 1 to 9. So initially have the idea, then do mock-ups, and do some prototypes, do some testing in laboratories, in a component level, then you have an integrated testing, then you have a more complex testing in a relevant environment, and do testing in space, and eventually you can operate it in space. So during this process, you have an idea that you have a baseline where what you want to achieve, saying I want to do a mission and want to measure certain things. So I know what level of fidelity I want to measure that thing. So in that case, that's my baseline. And as I start developing it, sometimes I encounter problems. So if I encounter problems, I could throw it back to the previous stage and say, okay, I have to modify something, change the assumptions, change the performance parameters, and then go further. And it can take time, it can cost some extra money. And as you march down, eventually you're still hoping that you develop the mission to the level, at the baseline level that you hoped for in the very beginning. Sometimes it becomes a little bit better, so you design something, develop something that performs better than you expected, which is always a benefit. But sometimes it doesn't perform that well, because we always try to do something new, something that haven't been done before. So therefore, as you are developing it, realize it doesn't perform that well, even if I try to kind of modify it a little bit. So eventually I end up with something worse than the baseline, but then you have to design if it's good enough or not good enough. If it's good enough, you're a little bit below the baseline, but you're still above the threshold, so it's good enough. But if it's going below that, then you have to decide, this is really worthwhile, keep developing it, but just say, I don't think we can do this, so let's forget about it. So throughout this process, your mission ends up somewhere and deliver the science that you're hoping to do. So as you are designing this, you have this circular development approach saying, I have an idea what I want to do, and I create something, create a prototype, create some kind of artifact. And that's the sense-giving part of the development. And this is kind of a designerly approach for the problem. And then once you have this artifact interacts with the environment. A good example is I want to make the best bread in the world. So I create a recipe, create the bread, and put it out, and say, I want this bread to last for 100 days. And put it out, and after 2 weeks, it starts molding. It's like, this is not good enough. So you have a second part of this development, it's the sense-making part. When you look at it after a week and say, this is molded, it's not good enough. So you interpret the findings, the artifact interacted with the environment, and then you find that it's not good enough. So you change the recipe, you create another artifact, you iterate, and then next time it maybe lasts for 3 weeks. And it's still not good enough. So you keep iterating until you reach your goal, and there's a stopping criteria when you say, I think this bread recipe is good enough to create a bread that can produce the outcome that I'm hoping for. And then maybe it doesn't last for 100 days, maybe it lasts for 90 days, but my threshold is it's good enough. So in that case, I stop there, and I have a recipe that can deliver on something. It's the same for the science. You want to have a certain measurement. You try to achieve that measurement. If it doesn't perform at that level, you have to decide from a scientific perspective what is still good enough, and then develop towards that until you reach your goal. So again, it's a designerly approach for the whole thing. You have to have a conversation about the goals that you want to achieve. You also have to have a conversation within your team and then anybody who's involved about the means how you want to achieve this. Then you have the conversation about the design process, designing. Because maybe if you do something new, the current processes are not good enough. You want to create a new instrument, and the current kind of development processes are not suitable to actually test them. So you have to develop a new process, a new design approach, a new workflow, how to achieve the goal that you want to do. And then you have to create a new language within your team. And the new language is very important because that provides a shared meaning between different team members. Scientists speak very differently from engineers, from managers. And you have to coordinate the interactions between them that they understand each other. A good example is that at JPL there were two groups. One of them, they were working on the Mars rover. One of them was called something operability. And the other group called it usability. And the designers and engineers just didn't see eye to eye, and they just rejected each other's ideas. And the designer came along and said, look, interviewed both teams, and then what you call interoperability, they call usability. So it's exactly the same thing. And once they understood that they are talking about the same thing, they started to cooperate better and then develop something that actually was meaningful. So you have to have this shared language within the team. If you invent something new, then you have to maybe come up with a new word for it, a new description for that, because if you describe it in an old expression, the old expression has a lots of loaded meaning that people expect already something about it. They know if you have a loaf of bread, it's a loaf of bread, everybody imagines it. So if you develop a bread which is like 10 meters long, it's not really a loaf of bread because you tell someone it's a loaf of bread, they imagine something like this. So a new language helps you to create a distinction for that new thing that you develop, and then you can work towards that. So again, there's where design can help. So let's say a few words about boundary objects. So that was the preamble about design. So boundary objects were established by Susan Lee Starr and James Gossamer in 1989 through social sciences. And they identify 4 categories for a boundary object. One of them is a museum object. For example, I saw an exhibition about the history of barbed wire in America and how barbed wire was used to break up the prairies for farmland. And then throughout the decades, the design of barbed wire changed, and the curator of the exhibition used this storytelling device, boundary object of different barbed wires, how it developed over the decades. The other boundary object can be an abstracted object, for example, a map. I have a map, I come to a new city, and I get lost. I know where I am on the map, but I don't know actually how to get to the destination I want to go. So I stop someone on the street and say, can you help me to get to my destination? I don't know where I am. And they say, okay, you are here, and you look at that, turn left, turn right, and you will get there. And then this boundary object helped us to communicate around in an abstract way about the environment, and that can be very useful. The third object, boundary object, can be a physical boundary, state boundaries, for example, between Hungary and Austria. And there is a boundary, and there you can cross that boundary, and you can deliver goods back and forth. And the fourth one is a standardized form. For example, if you look at the space missions between the European Space Agency and the US, there was the Cassini-Huygens mission. Cassini spacecraft was designed by NASA, Huygens probe by Europe. And the idea here is that you don't have to exchange all the ideas about the design, background design principles for the probe and the spacecraft. You only have to identify the interface. You know, how you kind of screw the probe on the spacecraft. What are the lines going in for power, for data, and once you have this interface designed, you only worry about that. And you can develop your spacecraft and your probe independently, but making sure that they interact with each other. So these are very good examples for the devices that you can use for designing anything practically, including space artifacts. When I was doing my research at the Royal College of Art, I was thinking that maybe you can have different other categorizations as well. You can do something like communication about boundary object, communication for boundary objects, and for through boundary objects. I'll explain what I mean by this. About boundary objects is, let's say if I write about a space mission, the history of space flight in the 1980s, and then it's about. The other one is for, when I'm creating something that others can use. For example, Anish Kapoor developed the blackest black ever, and then developed this new color so other artists can use it for their own artworks. It's for. We did a project at the Royal College of Art on the Venus Space Watch, and the idea here was that using a watch as an object, as a normal everyday object people can relate to, tell the story of space exploration for the Venus probes using a watch. For example, we're 3D printing the, does it work? Hello? Not working. So 3D printed the housing of the watch. In the old days, out of titanium. In the old days, they used a block of titanium to carve it out from the block for the housing. For the window, we used a manual laboratory-grown sapphire. During the Pioneer Venus mission, they used the actual natural sapphire to polish it out. So again, they demonstrated that how technology innovation by creating lab-grown sapphire kind of improved our exploration capabilities. The next one was this woven, actually looking at the wrong thing, pressing the wrong thing. Much better. So the other one is this little circular thing, which is the face of the watch. It's a woven carbon. So the idea here was that now we are using a woven thermal protection system for atmospheric entry to protect the probes when they enter the atmosphere, and you have entry heating. And we are using the same woven carbon material here for the face of the watch. Again, it was part of the storytelling about how technological innovation can help space exploration and how we can communicate that information to the public in a relatable way. So let's skip that for saving time. And the next one is through boundary objects. I found the most important one, because during design processes, the teams can actually work on the idea that they want to develop, but also they use boundary objects for communicating among each other. This is an example of a lunar rover that they were doing at the Johnson Space Center, and it started with a couple of sketches. And the team can sit around and say, yeah, do you like this? Where should we put the window? Just put it in the front. Where should we put the door? On the side? Yeah, but maybe we could elevate a little bit. So in that case, well, this doesn't work really well, so maybe we can rearrange the whole thing. So initially start with sketches, and you improve the idea while you're also evolving the boundary object, but also evolving the idea as you are going forward. And then you start making some little mock-ups out of paper or cardboard. And eventually you start making some subscale models and then see how that works. And throughout this whole conversation, you evolve the idea and evolve the boundary objects as well. By the time you finish your design, you have a testable lunar rover. You also kind of evolve the concept as well. So for boundary objects, this new categorization about and for and through can help to frame the conversation about the whole development. Also, it can be spatially and temporally coupled or decoupled. I can have an idea and then create a boundary, sketch something, send it over to someone else who lives in a different town. They look at it and they don't like it, mark it up, send it back to me. And then it doesn't have to be concurrent, doesn't have to be simultaneous. It can get separate space and spatial and temporally. But while you're working with boundary objects, it can broaden the paradigm, broaden the ideas of the designers and the engineers who are working on the project, give you new options. Because if you look at an object and say, I like it, but I want to put some antennas on the top, and then maybe I put an antenna on the back as well. So by creating this kind of boundary objects, it allows you to kind of advance your ideas and create some new questions, new thoughts, and new configurations that can help the final outcome of your project. So it can also help to share ideas between different disciplines, between scientists and engineers, and it can promote discovery. So they are all very nice kind of devices to advance exploration, and designers are trained to work with boundary objects, to work with communicating between different groups, and then embedding designers into the teams can be very useful for the whole project itself. Speaking of that, let's talk about the JPL's Innovation Foundry. I spent a lot of time there. Most of my career was done in mission formulation when we were designing and proposing missions to NASA for funding. So the idea here is, the important part is, so NASA headquarters is getting the money from the government. And there's a whole complexity in how they get the money. But once they get the money, they have some ideas what NASA should be doing, and they provide the goals, and also they provide the funding, and working with JPL's program office to identify these goals and objectives and how much funding is available. Now, beside the program office at JPL, there's also line organization. Line organization is where all the peoples are grouped together. So the program office reaches out to line organization saying, I need 3 mechanical engineers, some trajectory specialists, some power engineers, and some scientists. And then the line organization provides these people for the project. And within this environment, the Innovation Foundry, they come together and they achieve the goals that they set out to do for the program office and with the people that you have to actually execute the project. And depending on the technology readiness level, or if it's a concept, mission concept, it's called the concept maturity level, you start developing concept from a very early stage called the A team, which is like a low tier. I will talk about what these teams are doing through the TMX proposal shop, and eventually mature the concept to a level when it can be proposed to NASA for funding. So the A team, as I mentioned, is the lowest technology readiness level program for CML 1 to 3. So I had an idea to maybe come up with some initial mock-ups and some basic level fidelity kind of testing, if it makes sense or not to do these kind of missions. So it was established in 2011, and it performed hundreds of concept studies. It takes a couple of days to do these studies. They bring in scientists, engineers who are relevant to that field, and then they kind of come up with some mission designs just to show that it makes sense to actually follow up on these missions. So designers can be embedded in these teams, so they can help to facilitate conversations within different groups, scientists and engineers. So in that case, they understand each other. They don't speak very different languages. Once they have an idea that this mission can be done, they can go to a next team called Team X, which is more involved. It takes about a week to develop this mission concept. And they usually based on analogies. So a big database on past missions, subsystems, what they were doing, and you can just pick and choose different components and put it together, design the trajectories, design the mission operation kind of parameters, and then demonstrate that this mission can be done. And because they have ballpark ideas how much these different concepts are costing, like components are costing, they can cost up the mission saying more or less it will cost you so many millions of dollars, which is very useful because then you can figure out if it fits into that ballpark frame that the program office would like to see, saying, I want to have a new Frontiers class mission, which is like $1 billion, or a Discovery class mission, which is like $500–600 million. So in that case, you can ballpark it saying, yeah, I think we can achieve the science goals achieving the goals. The means would be, this is the configuration that we want to do, and the cost is this is more or less how much it's going to cost. But it's still based on analogies, so it's not really fine-tuned. It's just a ballpark idea what we can or cannot do. So once we have that idea, and the program office thinks that we can go forward to the next level, we can start proposing it to NASA, then you go to a proposal shop, and that's a very dedicated team. I used to run these teams with a group of scientists and engineers and financial folks. And then the idea here is that we spent about a year or maybe 2 years to do a point design for the study and work out everything to the finest detail about how this mission would look like. What is the science you want to achieve? There is something called the science traceability matrix, which goes from the mission goals down to the performance metrics, what kind of instruments you want to use, and how to operate them. Got to the mission traceability matrix saying, then if you put that instrument on a space mission, then the mission have this kind of rocket, this kind of body configuration, these kind of antennas, and how that operates. So this traceability is very important because then you can figure out if the mission is working correctly or not. So again, when you have designers on the team, they can help the team to coordinate between scientists and engineers. So in that case, they understand what they each other are talking about. But also, it's very important because when you write a proposal, then you have to write in a way that they speak with one language. So you bring in strategic editors who go through the science write-up, the engineering write-up, the management write-up, and make sure that it's kind of harmonious across the board. So in that case, not like you have to have specialists to read certain areas. And then you have very nice graphics, like Keystone graphics, so people can look at it. It can be glanceable, so you look at it and understand the mission concept right away, mission operations right away, and then you have call-out boxes that kind of summarizes the key aspects of the mission. So when you go through a multi-level reading, you can flip through it, read the highlights, look at the figures, and you have an understanding what it is. But then you can go deeper and look at all the text, and then you have understanding of the final details as well. If you have specialists who want to understand if it's working or not, they can look into that. So designers can help with this because then we are writing a sales document to NASA headquarters saying this is the mission we are proposing, and from this you would understand exactly what we are talking about. We are not talking about a slang kind of approach. We are talking about a very well-written proposal that they can use to decide if they want to fund your mission or not. So beside the Innovation Foundry, there's a separate group called the Studio. It's a small group of designers and artists, and they were helping to come with outreach kind of activities. Sometimes they were embedded into mission teams, and they did the same thing I was talking about. But in general, they are a strategic asset to JPL and NASA because they help with the communication as well. They are, again, trained designers and artists who can help with that. So let's get that. Storytelling and Keystone graphics are important, as I mentioned, a key element of this because it has to be glanceable. This is, for example, Keystone graphics about atmospheric entry to Venus for a Venus balloon mission. When you enter the atmosphere here with the aeroshell, open the parachute, then drop the front shell, pull out the balloon on the parachute, inflate the balloon. Once the balloon is inflated and aeroshell is dropped, then you eventually end up at a floating altitude. And then in one figure, you can figure out the timeline, how each stage is going to take, what the sequence is, and then it's very easy to understand. So having this Keystone graphics is very important, and designers can help with doing that, and the storytelling. I talked about boundary objects. During the design process, designers can sit together and come up with configurations, modify the configurations. We have a bunch of Lego pieces there, and then people can just use Legos to say, put together a space skeleton, this is where the antenna goes, this is where the, the propulsion tanks are going, and then if you can figure out the configuration, and they can have points, counterpoints about maybe we could configure it differently, and eventually end up with a final configuration that can use it as a baseline for future developments. So, conclusion from this part is the Innovation Fund at JPL is a strategic asset to NASA and also to JPL. We're developing mission concepts and mission formulation phase from blue sky idea, I have an idea and I don't know if it's going to work, to the point where we can propose this mission to NASA for funding. And Innovation Foundry is using designers. They're embracing storytelling, embracing keystone graphics. The conversations are very important, and that's where human-centered designers can play a role. And also to facilitate conversations across different disciplines, and using these boundary objects, again, to facilitate these conversations. I mentioned that. So I'll get to the final stage, I'm running out of time, is where human-centered design can help human space missions. Because very often we design these missions and astronauts go up, they do their mission, they come back, and they get it done. Very important, they do a fantastic job. So currently, if you look at the International Space Station, it looks like that. It's like a factory. You live and work inside a factory, and it's a big mess. You sleep there, you operate there, it's noisy, it's smelly, probably you can tell about it, and it's kind of a mess. So if you look at science fiction movies, this is how we envision the future, that everything is very spacious, and then you can walk around, it's like a hotel in space. Getting from the current approach to there is a very big leap. You need lots of technical development, how to put mass in orbit, how to develop this environment, the gravity and everything, lots of complexities. But again, we are moving towards that in a way that if you move from exploration to exploitation and space tourism, eventually you want to have environments which facilitates towards space tourism. So in that case, you have to have more of an environment that's benefiting them. So that's, again, where designers can play a role. So if you look at Maslow's hierarchy of needs, he developed this concept saying, once you achieve a certain level of needs, you can go to a next stage, and the next stage, and the next stage. At the basic level, you have the metabolistic needs. You need the environmental control life support system to provide the air, water, and food. You need power, you need light, you need environmental protection, for the habitat. You can have the habitat itself, or you can have the spacesuit when you do EVAs, extra vehicle activities. So that's basic needs. You want to go there and you want to survive. Once that level is established and you have that, then the next level is you still have to have safety. You have to have a radiation shelter. If there's a high radiation environment of the sun, then you have to kind of escape from that and then stay there until everything is safe. You have to have space autonomy, different sensors and alarms that warns the astronaut that something is not right, and communication system, health monitoring. They're still the basic needs. And this is where we are currently, at approaching the basic level. But as you're opening up space exploration for space tourism, for humans, for everyday people, then you have to start addressing high-level needs, love and belonging. You are separated from Earth. The farther you go, the hardest it is to communicate back to Earth. If you go to Mars, for example, the round trip time is 40 minutes. If the Earth is on this side of the sun, Mars on the other side, it's 20 minutes one way. So if you need some emergency, you cannot just pick up the phone saying, can you help me? It takes 40 minutes, even if they answer right away. So therefore, autonomy is very important also, love and belonging. You cannot just talk to your loved one if you have a nervous breakdown. You have to have, some kind of way to communicate. How to design those ways, designers can help. Then you have the self-esteem, that positive control, feedback, respect, confidence. Again, it's a high-level need. If you have a short duration space mission, go to the International Space Station. Some of these high-level needs are not as prominent because you have constant communication back with ground control, and then after a couple of weeks, you can come back and everything is fine. But if you go far away, it's getting harder and harder. And then you have the cognitive needs, learning and learning and playing instrument and art and so on. Those are also very important. Currently, you can see astronauts going to the cupola and looking down, taking pictures. Fantastic, very nice. Or Chris Hadfield playing the guitar and so on. So you have a little bit of elements there, but for long duration missions, you have to address that and so on. So this hierarchy of needs is very important in a way that engineers, scientists can address the basic physical, psychological needs, but as you're going higher and higher in this hierarchy, then you have to have designers who come into the team as soon as possible, because you cannot retrofit something later on. You cannot design a space mission and bring in a design at the very end saying, make it human-centered. Because then you say, yeah, but it's already, everything is set. You should have done this and that beforehand. So you bring them earlier and then work with you and then develop the environments that's both functional from a basic physical, psychological needs, but also functional from a human-centered need where astronauts can operate. So when designers design something, you're creating habitat, some kind of interactive tool, some kind of environment. And then, so they're curating the environments. So basically, they're reducing the options that they have, astronauts have, in a way that they want them to experience the artifact, the object that they're working with, and also they want to use the object. For example, you don't want to overwhelm them with options. If you have a flashing red light, they have to understand that means danger. It doesn't mean that you are playing a game and you want to have some options, because if it's danger, it's danger. So you curate the options for the astronauts, but you train them as well. You work with them during the whole development, because they are the users at the end. And then when they go up, they know exactly how the environment will be interacting with them, how they operate. A couple of examples about learning, I mentioned that before. Privacy is a big issue. If you look at the space station, I don't know what your experience was, you can velcro your stuff to the wall and you sleep. But having privacy and having a kind of a personal space can be very important. So how to create that, how to set aside some room, what the functionality of the space would be, can be designed by human-centered designers. Creativity, I mentioned that before, for long duration missions especially, and relaxation, I mentioned the cupola, and ownership of the physical data. If you go off a long duration mission, everything is collected, your vital signs, your interactions, your data logs, everything. Who owns that? Astronaut? Will it owned by ground control? Will it owned by humanity because it's public record? How much privacy you have? It has to be designed in a way that it fulfills all the needs from astronaut level to agency level to human population level, to a public level. So human-centered design is very important for human exploration as well, especially as we go towards more and more of the space tourists and public accessing space level. We are creating these novel artifacts towards higher level needs, which has to be designed by designers, hopefully. We can curate the autonomy because you are separated from Earth. They are on their own, so when they interact with these objects, with the environments, it has to be designed in a way that they are functional both ways. You also have the privacy between them, the trust between the agent and the astronaut itself, both ways. Let's say if I'm sick and then an agent is kind of helping me to recover, I have to trust the agent that does the best for me, but also it has to go both ways. Also, if I go crazy, the agent has to act and say, I don't take your advice anymore. You saw 2000 Space Odyssey, and Dave, I cannot do that. And then override the humans, but you still have to trust the agent that it doesn't do any harm for you. So designers can help to foster these conversations between the ground control and the astronaut and the environment, and vice versa. And it's developing field, human-centered design, where more and more parts of the agency, from the science part and also human exploration part, can employ designers, human-centered designers, who can contribute to the success of these future space missions. So that's it. Thank you very much, and hopefully it was. Thank you. Any questions?
Thank you very much. What is great talk. We have time for questions, if we have.
Yeah.
Yes, hi. My question would be, do you see an openness for this kind of electric in Europe?
So do I see a possibility for the European side to employ designers? That was the question, right? In the future. So this is one of those. When I started working at NASA as a technologist, the approach was that when there is a budget cut, the first thing goes is technology development. And then later on, the first thing goes is designers, because you can still do the space missions without addressing some of these higher level needs. And, but sometimes you have a little bit of up, some little bit of down, but eventually, gradually, it's kind of improving and becoming better and better. So there is a group of designers called DISC involved with the International Astronautical Federation. We have a kind of a group meeting there all the time, and they have designers from all around the world, space-related designers from all continents. And we try to have some kind of momentum developing to organize among the community members, and then bring some attention towards design and how it can benefit space missions. And hopefully, with that, a little bit longer approach is that you can have two approaches to this, a bottom-up approach and top-down approach. Bottom-up approach is saying, let's get a designer on the team, and then to small design solutions, demonstrate that design can play a meaningful role in the future. The top-down approach is when you have an enlightened manager and say, I think design is important, and let's have designers on the team, and I order the team, the middle managers, to have some designers on the team. The problem with this whole issue is the middle management, because design is not part of the workflow. So therefore, when you go to them with a design approach, they can say, well, you know, it's not my job requirements, so I don't want to use it. If you go to top management, they said, why did you bypass the middle manager? So it's not good for you. So eventually, you have to have someone from the top level who says, I see the light, we need designers, make it so. And the middle manager is happy to do it because it's a requirement for the mission. So we have to work both from bottom up and top down, and hopefully, gradually, it will be part of the workflow.
Any other questions from the audience? Great. We don't have more questions. Let's thank again our speaker.
Thank you.
With that, now we will move to the poster flash talks. We will have a poster sessions, and we would like to offer the opportunity for all of the poster authors to give a 1-minute talk about their posters. For that one, we created a PowerPoint presentation. So we will do these poster flashlight talks in the following way. We will follow the order which has been published in the program book with poster 1 to poster 30. And I will right now switch on the computer for the poster flashlight talks presentations. I would like to ask the authors of the poster, I mean the one who will talk about the poster, to step and come a little bit further here in the front sides of the room. And everyone will have roughly 1 minute to introduce his or her poster. Just give me a sec to switch to the posters. And just 2 housekeeping remarks. It's really hard to present your work in 60 seconds. And the second thing is that we ask everyone to send 1 slide to us. We have not received 1 slide from all of the poster authors. So for those ones, we just placed a slide with their title. So there might be some white background slides in this poster flash talks. So let's see how the poster flash talks works in this year.
Hello, good afternoon. Let me introduce myself. I'm Peter Német, Honorary Associate Professor of Research Center of Space and Space Technology and Space Law at Széchenyi István University at Győr. Our research group is working to introduce students to the basic of radio astronomy using simple methods by leveraging the technical capabilities of Earth-Moon-Earth link established a few years ago, thanks our Zoltán Baj. By repeatedly reproducing the experiment and presenting it to wide audience, we are helping to popularize space research. Radio waves reflected from the celestial body closest to us can be effectively demonstrated in education, for example, when explaining the speed of light. We have to make some contacts via ASS2, and my top of my work was when we have contact with Tibor in the space. Thank you very much.
The next one, please.
Thank you. I'm Florian Vámosi from the Mate University. I'm a master's student in economics, and I also occasionally hold lectures in terms of continuous monitoring systems. We have done 6 balloon launches in the last couple of years, and I've evaluated both technologically and economically the outcomes, and we've captured a lot of nice pictures like this one. Please come to our poster and check out our work. Thank you very much.
Ladies and gentlemen, thank you very much for the opportunity and acceptance my poster to László. My name is Dr. Kinga Tamási, a Hungarian space materials engineer, coach and psychological student. And I have no luck because after this great presentation, I cannot say anything new about our project. But when I say that, in a nutshell, our goal is to protect the people who would like to explore our universe. That means not just physically, but mentally also. And my newest idea was like a materials engineer who can be adopt and who can be manifest the fractal structures in the interior, like a space architect design. The fun fact is my professor told me the fractal topic is really old school, but doesn't matter because our brain really loves it. So in the future, we would like to improve the 3D printing and additive manufacturing methods with space heritage materials. And if you have a question, please contact us near our poster. And what can I say? That enjoy your day. And if you have time and opportunity, please touch some nature-inspired surface near outside. So thank you very much. Enjoy your day.
Yeah, the next one.
Hello everyone, my name is Yahya Ibrahim. I am from Honran-Staki, and we did this project with Lechner Knowledge Center. This project is supported by European Space Agency, and what we did here is monitoring water appearance in 2 national parks in Hungary. We did this study for 4 years, from 2021 to 2024. And we have the map for water appearance in these 2 national parks for all scanning during these 4 years. We have some maps for monthly aggregated appearance of water, and also we validated our AI methodology with expert field studies during 2024. So the experts went to these points during this day, and we tested our algorithms. We have too many maps like this in the poster. You can come to see it, or also it's available on our website. And if you have any question, I'm at the poster section. Thank you very much.
Good afternoon, everyone. My name is András Mihály. I'm a PhD student here in the university. In my research, I'm mostly researching about quantum satellite systems and quantum satellite networks. And in this research, we propose a new model to simulate whole networks of, not simulate like analyzing of quantum satellite networks, because when we are introducing quantum into the satellite network, in some ways it makes it more really complicated, and in other ways it makes it easier to analyze by using some effects of the quantum entanglement swapping that makes the routes non-linear in time. At least it allows non-linear routing in time. And if you have any more questions about the research or about the data, feel free to ask me at the poster section. Thank you very much.
Sorry. Okay. So hello everyone, I'm continuing with the theme of entanglement, and entangled photon pairs are in practice produced by illuminating a specialized crystal, most commonly with some kind of a pump beam. If this pump is a plane wave, then we know that there is an exact analytical solution to where these photon pairs will end up. They will form a perfect circle. However, in practice, usually these crystals are illuminated with a focused Gaussian beam, which distorts the shape, and it distorts it in a way that cannot be analytically calculated. In our poster, we are giving you an approximation or in a closed form of the shape depending on the beam parameters of this distribution, and we validate it experimentally as well.
Hi, I am Emil Hödl. I'm working on attitude determination of Unity satellite. This satellite is a Packet Cube class satellite. This satellite uses onboard some models onboard, for example, the world magnetic model and orbit propagation model. We use some sensors, for example, light sensors, 3-band, and gyroscope sensor, and magnetometers. And we use 3 algorithms, triad, multiple extended Kalman filter, and quaternion estimation. And we all use this onboard the small satellite. The satellite size is very small. 5 by 5 by 15 centimeters. Thank you.
Hello everyone, my name is Benedek Csala. Traditional GNSS meteorology focuses on tropospheric delay or precipitable water vapor. Our study investigates the use of GNSS, carrier to noise density ratio, for precipitation field sensing. Our poster presents a measurement setup which facilitates the analysis of precipitation-induced effects on the GNSS signal. Also, we present tomographic reconstructions of precipitation fields alongside with the respective radar imagery. Our research highlights the potential use of C over N0 as for continuous precipitation monitoring. Thank you.
Good afternoon, my name is János Tanács. My research examines the Challenger launch decision event not only as a technical failure but also as an argumentative problem. During the teleconference on the 27th of January 1986, NASA managers expected engineers to provide a clear and defensible recommendation regarding launch safety. The vast majority of the literature focuses on the fact that the engineers were unable to find or to demonstrate a correlation between O-ring performance and low temperatures. But relying on some neglected historical sources, it can be said that the engineers didn't have a complete set of temperature data. So according to my reading, the real problem was that the engineers were expected to defend the conclusions stronger than the available evidence could support. So a broader implication is connected to what I call Gábor Zemplén's maxim, who is a fellow researcher of mine. If you would like to strengthen your argument, you should weaken your conclusion. Thank you very much.
Thank you very much. Hello again. I'm Florian Vámosi from the Mate University. And in 2020, we launched the weather balloon in collaboration with the local high school, with some high school students. And we found an interesting to us region in the upper atmosphere, which had higher than usual gamma and beta radiation. And to investigate that more, we have built our own Geiger counter-equipped data logger. And it withstood 3 launches last year. And we now have a finished design to put it into low-scale production. Thank you very much.
The next one, András Hegedűs, if he's in the room. Then we will continue. I don't know whether, yeah.
Thank you. Good afternoon. My research focused on last November solar storm and its impact on HF radio frequency band propagation. During the event, I conducted nationwide measurements in the 6 to 25 megahertz frequency band. The results were clear. Ionospheric disruption above 10 megahertz caused channel quality degrade rapidly, leading to a massive drop in usage. At the same time, the traffic below 8 megahertz has increased because the intelligent radio systems detected in the upper frequency band the anomalies and automatically shifted their traffic to the lower frequency bands. This sudden migration caused severe congestion and interference in this frequency band. Thank you.
So welcome everyone, I'm Orsolya Meyer and I'm a scientist in the WIA-E project, but today I'm representing the Orion Space Gens. This is our space seed mission with Genesis Space Flight Laboratories, and we are going to study the effects of long duration space exposure on different plant species. The seeds will be on sun-synchronous orbit for approximately 9 months in re-entry nanocapsules, and after coming back to Earth, we are going to plant and grow them in our vertical farm here in Budapest. And we are going to study the growth, the germination, and the plant stress responses. This study can help us develop resilient crops on Earth and also support future space agriculture. Thank you so much.
Another poster by the BMS Orbiters team. Let's move to Bernard.
Good afternoon. So if you ever wondered whether there is liquid water on Mars, or if you're now wondering why anyone would care, or how we could test that in reality, then please come find me at the poster session. My name is Bernadette Pál, and I work at the Research Center for Astronomy and Earth Sciences, and I use Martian modeling to see whether it is possible, theoretically, for liquid water to form in a very small amount on the surface of Mars today. Thank you.
Thank you. The next one.
Good afternoon. I'm László from the University of Budapest, and in my work I use the HFSS simulations of printed filters to study the possibility of decreasing resonator losses via using inverted suspended microchip resonator structure to enhance filter performance. My end goal is to design a very low cost and very high performance. Sorry, a bit clumsy. To create a method for manufacturing low-cost and high-performance RF filters for satellite reception. You can see 2 pictures. One illustrates the whole idea of forcing the electric field in an air gap instead of a lossy material, and the other is parts of the results. The green material the green curve shows high loss filter, and the red shows the same filter, but with my method. It generates an decreases loss. Thank you. You can ask questions from. Okay.
Next one, someone from that team. Yep.
Imagine a single particle of radiation crashing a plane or misguiding an autonomous car. Today, as memory modules continue to shrink in size while their capacity grows, this scenario is becoming a real engineering crisis. Their high bit density makes them more vulnerable. Or experiments research. Yeah, the results of our experiment, and also shows way to how to protect our electronics. Please stop by our poster. Thank you.
Hello everyone, my name is Máté Boda and I'm from Kuvasz rover team. We are a team of university students designing a Mars rover for the European Rover Challenge. Being a new team, we have limited resources. We don't have access to professional machines, sponsors, and we have limited funding. This means we have to use engineering judgment and compromises to save costs and still end up with a functioning system. We would like to tell you some about our solutions and the thought process coming up with them. Thank you.
Thank you. The next one.
Hello everyone. My name is Levente Kis, representing BMS Suborbitals. We are currently designing two key subsystems for Project LEAP. A student developed the modular two-unit CubeSat platform. On one hand, our team is focused on designing a highly space, energy, and cost-efficient attitude control system utilizing planar PCBs, planar magnetworkers embedded in PCBs. On the other hand, we are developing a lightweight yet structurally robust orbital control system powered by a metal 3D printed cold gas thruster. We invite you to visit our poster, where we would be glad to share our findings, the design methodologies, and our first test results, as well as showcase the initial prototypes of the two subsystems. Thank you.
Thank you. Next one.
Hello everyone, my name is Artur Balázs. My colleagues and I built a functioning fiber optic gyroscope based on readily available telecommunication parts. This device was flown on a sounding rocket to low altitude. The device remained fully operational during the flight after that. At some parts of the flight, it showed good agreement with the onboard MEMS gyroscope. At some other parts, it showed an inverted direction of rotation, but the rate was acceptable. So we think this is really promising and a good showcase for the application of telecommunication parts for sensing applications. If you would like to hear more, please visit my stand. Thank you very much.
Thank you. Next one. If the author is not present yet, let's go to the next one.
Thank you. Greetings, my name is Mark Kovács, and I'm a master student at the University of Pannonia, and also a sponsor of the ESA Academy and the IEEE GRSS, and the winner of the 6th Student Grant Challenge. And my winner proposal was a spectrum monitoring device that could be integrated into 1P, that's a 1 unit pocket cube payload. And my approach that differs from the previous attempts or results from the University of BMA is that it's built on a different architectural approach, and it enables reusability of the brains of the spectrum monitor, which is going to be a reusable system or module, and this enables integration into other small satellites such as pocket cubes and CubeSats, and existing platforms such as Project LEAP. And thank you. If you would like to learn more, please stand by at the poster. Thank you.
Thank you.
Hello, I'm Andrew, and I made a research about the pressure-dependent performance scaling of solid propellants. Generally, of solid propellants, we talk about non-composites and composite solid propellants. And usually, quite often nowadays, people choose only by the basically combustion temperature and the effective ISP of the propellants. And I try to point out that this is not exactly right, because, for example, in space propulsion, if we want to use solid propellants, there's a really big condensation problem at the exit of the nozzle. And basically, I did a comparative research, literature research, and try to show that how should we basically choose propellants depending on what mission do we want to basically do. If you are interested in this research, please see my conference paper and presentation. Thank you.
Thank you.
Good afternoon, everyone. My name is László Ábró. I'm a university student here at TU Budapest, and I represent here Project LEAP. LEAP stands for Low-Earth Adaptable Platform. It's basically a satellite project that builds on the experiences of students who gained experience in rocketry projects, including the avionics and payload subsystem parts. We are building an adaptable platform that could support university research project and may include some commercial use cases as well. What really stands out in our project is that we are designing a highly adaptable and fault-tolerant architecture based on the separation of the mission-specific and core satellite buses. Our project is now in the evaluation phase, which means that on the PCBs that you can see on the PowerPoint are being evaluated. You can see these prototypes at our poster as well. You are welcome.
Thank you.
Hello everyone, my name is Hussein. I'm a PhD student. I'm doing PhD on quantum communication. This work we present a novel quantum communication based on OFDMA. We use multiple quantum transmitter and quantum Fourier transform for multiplexing and also depolarizing channel. Then we use quantum state tomography for reconstruct the quantum, the received quantum state. Then we compare the fidelity between the received and the transmitted quantum state. I will be, for further questions, I will be in the poster session. Thank you.
Thank you. Next one.
Good afternoon. My name is Patrick Toth from Győr, from SASAT College. What does twin satellite mean? It is a 3PQ satellite in which BMA has a 2PQ and SASAT has a 1PQ. The Győr section of the satellite consists of 4 modules. The bed provides the satellite's power supply and stores the energy coming from the solar panels. The OBC controls the subsystems, the EPS controls the charge level of the batteries, the COM is responsible for the communication with the ground station. The aim of the mission is for students to design and build a fully functional 1 pico-size satellite that communicates with the ground station and the BMS satellite segment. The result of the experiment is that of the 4 satellites module we built, 3 are operational, even under space conditions. The communication module failed, but thanks to the twin satellite design, we can collect data from the Earth satellite modules, WIA-E, the BMI satellite segment. I am responsible for the ground station development within the SGAC College for Advanced Studies. Thank you for your attention.
Thank you. Next one, by Tibor Hegedűs.
Good afternoon. I'm Tibor Hegedűs from WIA Observatory of the University of Szeged. With my colleagues, we presented some examples how to do some physics from the semi-amateur, semi-professional meteor cameras. There are 12 all-sky meteor cameras over Hungary since the 2020s. And most of the observational data are used only for statistics and nothing else, or 1 or 2 times in the year the amateurs try to define the falling area of the very specific, very few meteor event. We selected 13 very bright fireballs since the last 3 years. And we analyzed not only the atmospheric orbit, but ablation theory. We studied how the mass is changing during the meteor flight. And also we tried to search for progenitors, asteroids, which can be the progenitor of these fireballs. For more details, please come to the poster. We are at the first panel, just in front of the door. Thank you.
Thank you very much. I don't know whether the next poster presenter is present or the next one. If not, I would like to give the floor to Victoria.
When was the last time you guys actually saw the Milky Way, like with your own eyes? Well, the Vega Astronomical Association has been trying for now decades to bring the sky closer to people in Hungary, from students to even professionals. This has been done through astronomical camps, an observational archive which collects both analog and photographic observations, astrocamps, sky parties, and also mentoring of students through various competitions like the International Astronomy Olympiad and also now CanSat. So if you would like to, see the sky for yourself and join a community where we are actually enjoying the universe together, then please come join me at the poster session and let's talk and let's connect. And if you would like to join this group of amazing volunteers, we are over 400 members by now, then we are absolutely welcoming you to join our little community here. And thank you. And let's have a good cup of coffee and a good chat afterwards.
Thank you very much. And let's give a big applause to all of the poster presenters. It's quite hard to give a 60-second flash talks, and all of them will receive this big applause from us. Thanks. And I just wanted to share with you that our program committee received around 60 abstracts for this conference, and since the time slots are limited, was limited either for this afternoon and for the day tomorrow. This is why we decided to have 30 poster presentations, and we made the decision not on the quality of the abstracts that we received. So this is why I recommend you to visit all of the posters during these poster sessions. In April, I had the opportunity to spend 3 weeks in the US at the invitation of the US Department of State as part of a special program named IVLP, International Visitor Leadership Program. I was there as a member of a group of 19 international experts participating in the IVLP, engaging in the Rising Space Nations program. We had meetings during these 3 weeks with different stakeholders across the US in 6 different US states, with federal government, state government representatives, with different space industry representatives. And one of the takeaway from these 3 weeks was that the most important part of the meetings are not always the formal parts, but the informal parts. So this is why we decided to have almost 1 hour for the coffee break here at the H-Space conference. I would like to recommend everyone to visit the posters, to have a cup of coffee, and to connect with the fellow participants of this conference. Having said that, we will continue here in the room at 4:30 p.m. and please enjoy the coffee breaks and visit the posters. Please come here and to copy your presentations.
Igen, egy perc. Szerintem idő van? Idő van? Igen. Ladies and gentlemen, it's my pleasure to open the session Science and Technology 1. This is the personal session here in this afternoon, and our first presenter is, as a highlight talk, Levente Dudás from the Technical University of Budapest, and the title of his presentation is Unity, the 6th Educational 3-Packet Cube Class Student Satellite at BME. Please, you have 20 minutes for the presentation.
Jó, hát szerintem 55 környékén én befejezem. Jó, nem, ez villany. Tábla, az a másik. Zöld tábla, kicsit föl. Nem, az a villany. A Kálmán. Az a villany, haló. Igen, csak a zöld. So good afternoon, everyone. My name is Levente Dudás, and I would like to talk about our satellite development called Unity, previously NMHH-1 3PQ class student satellite, like 5 by 5 by 15 centimeters size, and its overall mass is a little bit more than 860 grams. This packet satellite is here, no. So it's carrying on the LEO, so orbiting satellite, was successfully launched last year, 28th of November, with Falcon 9 rocket. And after one day, it opened the solar wings covered by solar cells and experimental side panels of the satellite. And till this time, we are now operating this satellite. So we are receiving signals from Unity and sending telecommand to the onboard system of Unity, and all of internal experiments, subsystems, including the main subsystems, the experiments by CANSAT teams, our special experiments on board the satellite are working very well and generating useful telemetry data to be able to calibrate it, to be able to operate it, and to be able to realize the control loops, for example, in case of the attitude determination and control system. This development is started in 2024. So these 2 years of development can form the whole satellite. The whole satellite contains several main subsystems, like electrical power system, which is the first main subsystem. The basic structure of this system, like solar panels on the wings, on the side panels, can produce incoming DC enough power to be able to operate the satellite. So before the launch, before August, the 1st of August last year, on the microwave remote sensing laboratory, we tested the satellite with opened solar wings here. And after that, we closed it with a special plastic wire. This will be melted up with some external resistors to be able to deploy the solar wings like these ones, and the special space-qualified antenna materials like bicycle brake bowden, quarter wavelength antennas to be able to communicate with the satellite. And then the outside view of the satellite, you can show here the different type of silicon-based Korean solar cells. These are cheap, very cheap. 10 times expensive, like the 3 layers or 4 layers, Azure Space type or Chinese replacement of this type of solar panels, solar cells. And we would like to measure these type of solar cells capability, how many DC power can be realized on board the satellite during the flight, during the orbit, during the lifetime of the satellite, and what about its degradation. And then the internal structure of the system. The first one, main subsystem, is the electrical power system in this part of the satellite. The 3 different ones containing these maximal power point tracking systems to be able to realize maximum incoming DC power from the solar cells, solar panels, and solar wings. It can form unregulated bus voltage on the system, and of course the power control unit can control this type of energy balance of the satellite. And then another PCB containing 2 different cold redundant, in this case hot redundant, onboard batteries based on lithium-ion type batteries, because we would like to operate the satellite on the dark side of the Earth. And this PCB contains 2 different 5-megapixel side onboard cameras to be able to monitor the Earth's surface or the moon from the satellite. And then the second main subsystem is the onboard computer. Not a single one, but it's cold redundant pairs, like cold redundancy, single point of failure structure in case of the OBC. This OBC, like onboard computer, is responsible for controlling the digital life of the satellite, including the main subsystems, power control unit, limiter switches, radio communication system, and of course the payloads. Not only our payloads, but the student designed payloads. And then the radio communication system is much more important because there is no optical wire and copper wire between the Earth station and the satellite. So we would like to communicate with the satellite on the 70 centimeters band. This means 437.39 megahertz, plus and minus 11 kilohertz Doppler shift on the UHF band. It uses single quarter wavelength bicycle Bovden type space qualified antennas, and it can realize 1.2 kilobit per second, 2.5 kilobit per second, 5 kilobit per second, more than 10 kilobit per second, and 25 kilobit per second digital data rate between the satellite and the Earth station. And this means it uses single GMSK modulation. And our experiments. The center point of the satellite containing this type of magnetic-based and motor-based attitude control system. The magnetic-based contains 3 different electromagnetic coils perpendicular to each other. Controlling the current of these coils, we can form magnetic field around the satellite, and an interaction between the satellite's own magnetic field and the Earth's magnetic field, it can rotate, it can pointing the satellite during the Earth's low Earth orbit. And of course, this time period, like time constant of this control loop, at least 1 pass, 90 minutes, 2 passes over the Earth station. So it's too small or too slow in time. And another one, attitude control system based on motor. Special switched reluctance motors are applied on the motor PCB on the satellite. And if we are rotating these masses here, here, and here on board the satellite, we can rotate the satellite and focusing, for example, the direction of the 5 megapixels camera to the right direction in some seconds, relatively. So it is working, but we have no control loop yet. But the sensor calibration of this system is almost completed last week. So we are now of this attitude determination and control. We have attitude determination, like sensor calibration. We are now knowing like the orientation of the satellite in time series, and we are able to create control loop in case of the motor-based attitude control and of course the magnetic-based one. This is a technological demonstration in 3 PQ size. And after that, we are mounted a lot of external experiments like onboard GPS here, special radiation detectors, the cumulative one like total ionizing dose measurement system, and the counter type similar to Geiger-Müller tube are mounted on board the satellite in an external PCB. And then another 1 PQ from the CESAT team at Győr. This will be in the next presentation. And of course, we are testing the solar panels, different type, gallium arsenide type, germanium-based, and silicon-based solar panels. And then we realized some external experiments. This side panel contains 10 different 45 by 30 millimeter size experiments. Some university students experiment. For example, our one, the first one, is the selfie camera. To be able to monitor how we can open the side wings, solar wings, and of course, the onboard antennas. After that, we took picture from the real moon, the real Earth, from the imaginary university. So it is a complex, not real, imaginary. So after that, we mounted on board the special resonant radar reflector experiment working on the 2.4 gigahertz microwave X-band, because it is very interesting when from Earth station we are illuminating with continuous wave signal on the 2.4 gigahertz band. This resonant radar reflector can reflect the electromagnetic waves backscattered back to the Earth with the switched pin diodes on the RF chain of this system. And if we can sense this type of pseudo-random binary sequence with a specified data rate, and we know its code, we can detect the satellite without any radiated electromagnetic waves from the satellite. It is a special backscatter radar type experiment. And we have some space on this PCB. I mounted the WLR radio communication module of the CANSAT teams to be able to communicate in the 868 megahertz band with not only GMSK modulation, but LoRa type linear FM chirp modulation, eliminating the high gain antenna of the ground station. And of course, we formed the international cooperation between UK SGAC team realizing integrated circuits on board the satellite, and we have an experiment from Serbia, like an international cooperation. And then the main advantage of this system, the external panel, opened side panel, contains 6 different CANSAT experiments. These CANSAT teams are secondary school students formed teams. In 2024, these were the finalists of the Hungarian CANSAT competition. The CAPISAT experiment is a multispectral light detection on board the satellite. It is working. The second one is Celeritas, like it is measuring the gamma radiation with a special photodiodes and scintillator on board the satellite. It is also working. Kulinsat is testing onboard memories, different type of onboard memories. It is suffering from the radiation from the sun, from the space, and the stored data is known previously, and it can sense some bit errors on board the onboard memories, and which type of memories will be the winner. Onsite realized a special Gale type radiation detector. It cumulates the UV and X-ray radiation, and after that the resistance of this special material can decrease. It is also working. SEED team realized MEMS-based and optical-based movement sensing of the system on the side panel. It is also working. Seraph measuring the different type of thermal coated by different materials, thermal coupling and thermal conductivity between these different points of the PCB, and during this measurement, it is also measuring the incoming lights. It is also working. Secondary school students' experiments are working now on Unity. The temperatures on board the satellite is relatively realistic range. Like the side panels, meaning solar wings, and the opened, deployed experimental PCBs is at least 100 Celsius degrees fluctuation. it is in sunlight, the temperature is increasing up to 55 Celsius degrees. If in the dark side, these side panels are cooling down to minus 60 Celsius degrees. Internal systems, like the temperature low pass filter, means the OBC and the battery PCBs inside the satellite can suffer from relatively limited temperature ranges, and its expected value is near the room temperature. It is good. So this satellite is working now. We are operating from the primary ground station of BME. You can track the satellite and receive the signal with this station. It is not necessary to have at home 4.5 meters diameter of dish and special X and Y axis antenna rotator. And we are operating now web-based software-defined radio. You can see the signal, you can hear the signal. This waterfall diagram can show like the incoming data packets from the satellite and the telecommand signals of the satellite. Real-time data, telemetry data can be read from this web page. And of course, we are operating the satellite, sending to the onboard computer via the radio communication system telecommands, and receive the satellite telemetry. And if we are refreshing the onboard firmwares, for example, on the onboard computer, the power control unit, the communication system, any different attitude control system, or the control loop will be the realistic one, and we want to refresh the onboard firmware of the satellite, we are sending firmware upload to the satellite. And after reboot the system, we are now operating a new firmware. And it is working. You can download the public open source demodulator and decoder software from GitLab, and please receive the satellite signal. And that's it.
Please, any question? No question. Thank you very much. Thank you, Renate. Thank you. Our next speaker is Ágoston Szűcs from the Space and Defense and Space Law Research Center from Győr, Hungary. The title is The Energy Supply for the First Twin Satellite of Győr. Please, the floor is yours. Let me put it here.
Good afternoon. I'm Ágoston Szűcs, and I'm representing Széchenyi István University and SESAT colleague for Advanced Studies at University of Győr, Széchenyi István University, and also Space and also Defense and Space Research Center at Győr. And it's a pleasure for me to introduce you our work and my presentation regarding the energy supply for the first twin satellite of Győr. Can I have your help, please?
at CESAT colleague, we got the opportunity to take part in MRC 100 satellite project, and we developed a subsystem which was capable of operating properly at the satellite's lifetime. And by this success, we used our gained experience and knowledge to go further and to develop our own satellite unit. And after that, we got the big opportunity to take part in Unity satellite project, where we developed an independent satellite unit, which is sized by 5 by 5 by 5 centimeters. It's independent because it has its own electrical power system and also onboard computer, communication subsystem, and also the battery subsystem. I want to present you the electrical power system and the components of it and the development process. At first, the electrical power subsystem is very important because we want to power our subsystems while the sun reaches the solar cells, and when we are in the shadow of the Earth and the sunlight can't reach the solar cells with using our battery. Here you can see at the left, you can see our first module in the MRC 100 satellite. At the middle is the Unity satellite, and the right picture is also the Unity satellite in the assembly process. Here I show you the topology of the energy supply of the satellite unit. The energy supply can be divided by electrical power subsystem and the battery subsystem. And the electrical power subsystem can be divided by both the voltage regulator and converter subunit, and also the energy management subunit. I worked mainly on the voltage regulator and converter subunit, and also on the battery subsystem. The voltage regulator and converter subunit has two main goals: to regulate the solar cells voltage, and to maximize the energy from the solar cells, and with that provide the subsystems with proper voltage levels, and also charge the battery. This subunit is contained by three main parts: the step-up converter and MPPT circuits, the lithium-ion battery charger circuit, and also the buck-boost converter unit, which is to make the proper voltage for all the subsystems. I made for every part, I made test panels for every part, and I made for these test panels after I selected the proper components for every part of the voltage regulator and the converter subunit. And I designed it to make our tests better. I designed these test panels. After that, I made measurements on them. Mainly, I investigated, I made the measurements to see these test panels after to see the effects of the input voltage, and also to determine the difference between the accepted proper operation and to investigate the problems. And after that, I had to come up with a solution for the problems we specified. And also we made not only individual tests, but integration test where I connected all those test panels with and without battery to have a look on this system, how can be these selected integrated circuits and circuits, how these units work together. After determining the problems, we made our full, complete electrical power subsystem panel, which is one panel, and also we made measurements and tests on all the functions it has. Now, let's talk about the battery subsystem. I designed this subsystem for 3 reasons. The first reason is to mount our battery on the panel, and the second is to protect our battery from overcharging and over-discharging, and also to measure its temperature. Firstly, to mount our battery on the panel, we had to use a copper cover, and we had to solder it on the panel, and I increased the copper filling on the panel, which makes our fastener force bigger, and we covered the copper cover with Kapton to earn not only electrical but temperature isolation. And we made the battery protection unit because the overcharging and also the over-discharging the battery negatively affects the battery lifetime and also the capacity. Here you can see the circuit of the battery protection and also the selected integrated circuits. And we know that lithium-ion batteries are very sensitive to temperatures. We also measure the temperature of the battery, and after getting data about the battery's voltage and also the temperature, we can determine how our battery is reacting the temperature changes and also the temperature itself. Before our battery selection, we made tests on the battery. Firstly, charge and discharge tests, where I measured the charge and discharge current and also the voltages. And these tests were it needed so much time. I had to automate the measurement system with proper instruments and a personal computer with a special program on it to handle all the instruments, and also an embedded system to change the battery state from discharge to charge and charge to discharge. I made also self-discharge measurements on previously tested batteries and factory new batteries to see changes, what affect the charge and discharge test made. And as for the results, we were able to measure our ampere-hour capacity of our batteries, and also we were able to tell the proper voltage level between the battery is safely can be safely operated, and that is how we designed our battery protection unit. We got a lot of knowledge about this project, how to design our systems, like firstly select to make a topology, after that selecting the blocks, selecting the proper components, and make test panels, make measurements, and the final panel make other measurements and improving our design. And this project was a very good opportunity for us to learn how to develop a satellite unit. And the conclusions were that we find that the solution of dividing the tasks to smaller tasks is a very good opportunity for us. It makes the development easier, and to follow the steps of the designing, testing, the evaluation, and also the making improvement our panels and systems. And also we had to come up with new solutions. And after we get our data from Unity satellite, we can say that the energy supply of the year twin satellite is working properly. Now our future plans to use the circuits what we made and were successful for our new project for the first year satellite. And after this, we want to help students to learn about satellite development, and that's why we joined to the Hungarian Student Space Program. And from the Defense and Space Research Center, we are providing technical and also project management support for the program. And thank you very much for your attention. If you have any question, then I encourage you to ask me. Yes. We made several types of measurements, an extended voltage range and a shortened voltage range to see if the extended one can damage or not our battery because of the high voltage and the lower voltage. And we made that we can say that our measurements are aligned with the available literature according to the lithium-ion batteries, that if we use an extended one between 2.8 volt and also 4.1 volt is a proper way to use our battery, and we will not damage our battery in this range, and that's why our this charge and discharge measurement were very useful to know more about our battery. Thank you.
Thank you very much.
Thank you.
Thank you, Adam. Thank you, Ágoston. And our next speaker is Ádám Mosonyi from the Technical University of Budapest, and the title is Development of Compact Autonomous Biological Sample Measurement Device for Sounding Rockets. Please, Ádám, the floor is yours.
Hold it, yeah. Thank you. Everyone hear me all right? Yes? Okay. Okay. Hello everyone, I'm Ádám Mosonyi from the team WIA-E Suborbitals, and today I will be talking about an autonomous biological measurement device that we developed for last year. So a bit about the team. We are a rocketry team at WIA-E with more than 100 members. The presented project was carried out by the payload team. Our main goal of our team is to compete in the European Rocketry Organization's Euroc Challenge every year. And for last year, we developed a 2U payload that housed the measurement device in question. So a bit of experiment background. The idea for the experiment came from Semmelweis University. The goal is to test the interactions of the astronaut bodies with the high G, high forces that acts on them during a rocket launch. We not only needed to prepare the bacteria samples ourselves, but we needed to keep them cold prior to launch and heat them up to human body temperature during launch. You can see on the image you can see our CubeSat. The top part housed the experimental module. Under that we had an independent optical experiment, and below that we had our onboard computer and power supply unit that were ancillary to making our goal possible. On the exploded view, you can see how compact the measurement device itself had to be. That works. Yeah, you can see that was the actual measurement device that housed the samples. It was surrounded by insulation panels, 3D printed insulation panels, and it had a main board that worked in tandem with the daughter boards to control them. You can see one of the daughter boards soldered to the flexible heating panels that were used for temperature control on the left side. On the right side, you can see a side view of the light path that the light would take in our instruments. Our daughter boards communicated with the main boards and received power from it. And our main board, through our OBC, allowed the telemetry downlink during integration. You can see the electronics now. On the left side, we have the main board. That main purpose is to connect the daughter boards to the rest of the system and to act as a backup data recorder in case something were to go wrong. On the right side, you can see the front and back side of our daughter boards. We had 3 of those inside the CubeSat. Each was responsible for measuring 3 samples and controlling the temperature of those 3 samples. On the bottom left, you can see our flexible heating panel. It's a single-sided flexible PCB with a long track to act as a resistive heater for temperature control. And on the bottom left is the LED panel that we use to illuminate the samples to allow for our optical measurement. In total, we had about 16 PCBs inside the device. For our samples, we had 6 E. coli samples and 3 water calibration reference samples. They were held inside 10 mm standard cuvettes, and they were sealed inside with a 3D printed TPU plug. The temperature of each sample was measured individually with a submerged NTC thermistor, and the samples were kept as cold as possible, or at least as protected from the outside heat as possible, by these insulation panels. The insulation itself is a glass fiber silica-based insulation, so it was very nasty to work with. So we had to seal them away to allow us to work on them without PPE. And these side panels also had also acted as the mechanical fixation of the inside measurement device. We validated our measurement methods on the ground with the device you can see on the left. On the right, you can see the correlation between our measurements with our device and laboratory equipment. These measurements were done with different dilutions of methylene blue solution, and we had very reasonable correlation between ours and laboratory systems. The optical density is measured by the light transmitted through distilled water compared in relation to the light transmitted through the solution being measured. You can see the temperature. So this is during launch day. you can see the temperature climbing steadily until we activate the heating. Then it rose rapidly, but we didn't get the nice stable 37 degrees Celsius that we were looking for, but we did manage to heat the samples up properly. And you can see some outlier results. Those were due to contact issues with our NTCs. These are voltage readings from our ADC sensors, from our analog to digital converters from 2 different cuvettes. On the top one, you can see one of our worst results. The primary reason for those results is because air bubbles were inside the cuvettes, and as the rocket was being integrated and assembled, it was being rotated, moved around, and the water bubbles impacted our measurements quite heavily. On the bottom, you can see one of our readings where we didn't have any bubbles inside the sample, so that was really nice and stable. We had water samples. The primary objective with them was to act as a moving calibration aid in case of temperature drifts, affect our measurement system. And you can see temperature did affect our measurement system quite heavily, so they were definitely necessary. But there's also quite a big difference between the two of them. So individual calibration of each measurement slot was also needed after the fact. So a bit about conclusions. During the flight, our main parachute didn't open correctly, so we landed quite hard, about 100 kilometers per hour of impact speed. Our experiment module survived relatively intact. We had minor damage to the insulation panels, which is to be expected with the very thin walls. And we also bent the bottom aluminum plate that everything rested on top of. But that wasn't the main reason our results stopped coming in after landing. Our battery module broke itself. The battery itself broke. Oops. The battery broke the PCSU board, and the connectors also aren't supposed to look like that. So that was the main reason why our results stopped right at landing. In the future, this system could be used for remote areas, in space, or for automated measurements, because sometimes you have to keep the samples at a certain hot temperature, and then you have to take them out of the heater, put them in the measurement device, and back into the heater, and this could alleviate that friction point for biological measurements. And thank you very much for listening.
Thank you, Adam. Some questions? Any questions? Yes? No, thank you. It's my pleasure. So thank you, Adam. The next... Our next speaker is Máté Magó from the Technical University of Budapest. His title is In Orbit Investigation of Passive Thermal Control Coatings, the Seraph Experimental Payload on the Unity 3PQ, so 3 Packet Cube satellite. Yes, please. And on the Corel. So, so we have 2 presenters, please.
Okay. Hello everyone, I am Máté Magó, and this is Anna Horel, and we are going to talk about the in-orbit investigation of passive thermal control coatings. We are first-year students here at BME, but we designed this experiment while we were still in high school, when we were given the opportunity to develop an experiment aboard the Unity satellite, thanks to our achievement at the CANSAT Hungary 2024 competition. we designed this with our third teammate Zsigmond Csaba, who couldn't be here today, and our mentor was István Seres, our high school physics teacher. So our experiment consists of two thermal sensors located at the top right and top left of the panel. And in between these sensors, there is a light intensity sensor. And the panel is controlled by an STM32 microcontroller. And besides that, we also have a lot of debugger and programmer ports on the board. And the panel is connected to the Unity satellite via the vias at the side of the panel on both sides. And the whole design was designed in KiCad. The program code is written in STM-CubeID, and each data packet is a 16-byte data packet, which contains the first temperature measurement, the second temperature measurement, the light intensity measurement, and the time since the start of the program. And these are all 4-byte data packs. And our code also allows us to send up 8 bytes of data packets to the measurement board, with which we can change the interval between the measurements, and we can also check for status updates. So that's how our final panel looks like. We can see that the one thermal sensor is painted with black epoxy coating, and the other is with transparent epoxy coating. And we had to test our panel under extreme conditions. On the left, we can see that we tested it in an industrial freezer at -40 degrees, and on the right, we put it in an oven at 100 Celsius degrees. In both of these cases, the board measured everything correctly, and there was no data loss. And we also had to validate and calibrate the sensors, which we did. The panel also had to go under different measurements to prove that the experiment complies with the requirements of the Unity satellite. These were, for example, weight and power consumption measurements. Now Anna is going to talk about the goal of our experiment.
So the main goal of our experiment is measuring the intensity of heat change on different colors of epoxy and examining the effect of heat on them. Also, we measure the effect of UV degradation on the transparent coated sensor. So when we do this, we compare the data to the black coated sensor and use that as a reference. We make diagrams from the data, and we can measure the thermal inertia from the beginning of life to the end of life of the white epoxy, and see when the degradation started to turn this color more yellow. So here we have the data. So this is the heat data. The orange color one is the see-through sensor, and the blue color is the black sensor. The temperature is within the calibration, and so we can see that we measured correctly before the launch, and it works. Below that is the light data. We can see that it goes up to 10 million milliwatt per square centimeters, which is the limit of our sensor. So this is when the sensor is facing the sun. And that's what we really need from this data. Below that, we can see the difference of the black and white sensors. This data is from January 8th, and this is a longer period of time. But now here are two single cycles. The first one is from the data below, and the second one is from a few days ago. We can see that the first one has more of an M shape. It's because the satellite back then was rotating more, so we had less stable data. We have so about the cooling down of the sensors, we have the conclusion that the black epoxy is cooling down much slower than the see-through epoxy. And about the heating up of the two sensors, we don't have definitive conclusions. Now, we also have, about the UV degradation, we can, so we measured that here. You can see that it's about 3/4 Celsius difference, but on the second measurements it's now about 1/2 Celsius. This means that our see-through coating is turning yellow, so we can really see the UV degradation over time. And if we'll have more data, we'll be really able to compare them when it's getting more similar to the data from the black coated sensor. Thank you for your attention.
Thank you, Ivan and Mate. Do you have any questions, please? No? Thank you again for your presentation. And our next presenter is István Sütő from the University of Szeged. The title is Raman Microscopy for Monitoring Calcium Carbonate Formation in Microgravity.
Can anybody hear me? Everybody? Okay. Thank you. Okay, let me just check the pointer. Okay. Okay, so thank you for the introduction. So we were experimenting with a very special reaction, especially in the case that two liquids forms a solid. Our reactor were a flow reactor, so we separated the two reactants in space and time. From the top, we were monitoring, gathering the Raman signal, and from the side, we were creating images. Here you can see the top view of the system. We used the simple valve system to fill up first the reactor with calcium chloride, then wash out the remaining to avoid any clogging. After we injected sodium carbonate to the rectangular gas capillary. As you can see, one of the precipitation changes, but it's not just the flow rate. Other parameters can strongly affect
not just the distribution, but the size and morphology of this reaction. For morphology reasons, with commonly used imaging, we cannot distinguish the polymorph of calcium carbonate. Here I show you the CEM images of calcite and waterite. As you can see, based on these images, anyone could distinguish the two only based on their shape. But these particles are really small, so we decided to use Raman microscopy to distinguish these. For us, the previously mentioned two polymorphs are interesting because aragonite is the third polymorph, but it's not really produced in these conditions. So there is a fourth possibility, the amorphous type. It has a really similar spectra than calcite, only it has a very, very wide peak at lower wave numbers. Between the two spectra, you can see that the characteristic peaks are different in height and width, so it would be very promising to use this technique to distinguish the two. Microgravity experiments can be made different ways. Our goal is to use a sounding rocket experiment, so we were making everything towards that goal. And first we used a parabolic flight experiment. We constructed a so-called Raman probe, which already flew in 2024. For the sounding rocket experiments, as you can see, we have a lot more time window for microgravity, and for that we are preparing ourselves, which is scheduled for 2027. So first I would like to introduce you the Raman probe. It's a very simple and robust design. I always start from the excitation part all the way through the detection. So the laser was fixed at the top here, and we used a drilled mirror to so we position the laser so the laser beam can pass through this drilled mirror onto this lens, where the laser beam gets focused onto the sample. After the scattered light is collimated by the same lens, it's reflected into a notch filter where the excitation wavelength is removed, and the rest of the signal is focused into an optic cable, and it's patched into a spectroscope. So this is a very compact and so it was made from aluminum, so its weight and its stability makes it perfect for microgravitational measurements. So these are the spectra we were taking with this system. First, for a solid sample, it worked very nicely on solids. We can see all the characteristic peaks, and based on this spectra, I can tell you this is calcite for sure. But in suspensions, because of the size of the particles and other factors, the light was scattered between the particles, and we had a very bad noise and signal ratio. After measuring the system with industrial Raman spectroscopy, we realized that under 100 micrometer particles will be invisible for our system. So that's why we decided to build a microscope. For designing a Raman microscope, first you have to select the correct optical elements. For that, we used a very similar methodology what they use in fluorescence spectroscopy. First, we select out our excitation wavelength, meaning the laser. So we clean up the laser signal, and only that can excite the sample. After that, we implemented dichroic mirror, but the dichroic mirror only reflects the excitation, but it's not steep enough. So we implemented also a filter, and the second dichroic mirror is splits up the signal into two. For the lower wavelengths we used for spectroscopy, and the higher wavelengths were used for imaging. So here is our Raman microscope, which we are intending to use for sounding rocket experiments. First, you can see the laser here. We implemented also an expander here, because if you expand the laser beam, you can focus it much more. Here is the dichroic mirror, which reflects the light onto the microscope objective. It focuses onto the sample. The scattered light is collimated by the same objective. It goes through the dichroic mirror onto the second filter. The second dichroic mirror splits up the signal. The two blends creates an image onto the camera's chip. The rest of the signal is coupled into a very interesting optical cable, because it changes a circle into a linear. It's very good because the spectroscope has a slit. That means it accepts a linear signal. So here are our results. As you can see, we see the three characteristic peak. From this spectra, I am able to tell you that it's calcite again, but from the image we took, I won't be able to, because the particles are small. That's why it's very good that we implemented Raman spectroscopy as well. As you can see, it's a magnitude better signal than before, so it's much better. Also, on the picture, I showed the laser spot. So this is the only spot where the signal is coming from. So sorry, one more. So we also managed to measure one crystals by using a 20-time magnification objective. Here you can see that based on the SEM pictures, this is calcite and this is vaterite. And as you can see, using the most intense peak, we were able to distinguish the two polymorphs. These crystals are approximately 15 micrometers in diameter, and we were very happy that we were able to build such a good setup. So in conclusion, we were able to construct a Raman microscope which can distinguish different calcium carbonate polymorphs. We have characteristic signals from suspensions, and we were able to measure particles above 10 micrometers in diameter. I would like to thank for my supporters and also to you for your kind attention.
Thank you, Sven, for meeting the time limit. So, any questions? Not yet. No, thank you again.
Thank you as well.
Okay.
Could you help me remove the microphone?
Our next speaker is Peter Vana from Budapest. The determination of satellite rotation periods using optical tracking observations. Peter?
Hello everyone, my name is Peter Gábor Bana. I'm independent software developer and sole proprietor And today I'm bringing a topic, determination of uncontrolled satellite rotation periods using optical tracking observation. It was a cooperation work with several authors you can see on the slides. Can we play a short video? No, no video, okay. This presentation about actually to end process, how we observed uncontrolled satellite on the sky and observed by the ground telescope, created light curves, and from the light curves we try to figure out what is the estimated rotation of the satellites. Okay. This topic is related to the space debris problem. This is a bigger problem in the space because more and more spacecraft is up there, but after end of the operational lifetime, they remain around the Earth, and they can damage other satellites or spacecrafts. And the other problem that these satellites have to execute collision maneuver executions. Így jobb, hogy beszélek. Collision evidence maneuvers, which means more fuel and more money from the operators. This picture is from the ESA report. Is the statistical distribution of the space debris around the Earth. I would like to highlight here some note. The ESA has the zero debris approach. They try to clean and keep clean the space. There is active and passive protections. The passive one is the shielding against the space debris. The active one is how can we remove actually these unused, uncontrolled satellites. The geosynchron orbit is very important because on the Earth we have only one, and there can be found the telecommunication broadcaster and weather monitoring satellites. But before we can remove such satellites, we have to understand better this orbital dynamics of these debris. And it's not easy because several facts influence the behavior of such objects, like solar activities, gravitational fields. So it's an open topic, and it's quite expensive to go up there, get a satellite that approaches the debris and get some data. It's easier and cheaper ways, it seems so, to do it by ground telescopes. And by the ground telescopes, we can create light curves that you can see on the diagram. And from the light curves, with mathematical methods, we can get data like dynamical, rotational, physical properties of these objects, size, albedo, shape, composition. Here, for a fast blink up, I show you a rocket upper stage as it is rotating. It was made by the Astroscale Japan satellite, made this approach, and it looks like that this debris actually is rotating not only on one axis, but on 2 or 3 axes. So its rotation is complicated and complicated to catch and remove from the space. We use the Pan-8 telescope. It's in the WIA. It's satellite and space debris tracking the observation telescope. And from my point of view, it was important that it can generate raw data, XML data actually, that hold several metadata like NORAD ID, GPS data, whatever, and the brightness data like exchange and declination magnitudes. I've created a light processing program that can import such raw data and then execute the maths like normalization, rectangling, filtering, and execute several frequency analysis methods. And after that, we can tell something about the period estimations. Here is the math behind the full story. There are several steps. How can we estimate the rotation period of such uncontrolled satellites? The first step is the data filtering. We have to remove the outliers. It's on the diagram, is the gray points. They do not belong to the objects, actually. I use for that the sigma filtering and machine learning algorithms. The second one is the detrending, that these light curves can hold the slow brightness of the data, which we have to remove for the good quality of the results. I use for that the Savitsky-Golay filter with a good chosen trend window. And the third one is the period estimation, where I used several frequency analysis algorithms like the Fourier, fast Fourier, Lomskarg, string-length, Fierce dispersion, minimalization method, and the clean. And at the end, at the verification, I created phase diagrams when we can fold the curves on each other and see how the collapse is each other, and so we verify the result. And the mathematically way we can fit 8-degree Fourier curve using this OC root mean square method. The root mean square of the residuals can actually tell, it summarizes the quality of the fit into one single number. Here is a concrete case study. This rocket stage was measured in the last year. It was launched in the 97 from Soviet Union, and by the program I can generate the more wider diagrams. Where was this rocket stage headed? The strength of the magnitudes, it's for checking purposes. And the third one is the important for us, this is the light curve. The diagram seems from the program, just for a fast blink up of the Lomskarg periodogram, try to identify the periods. And the bottom one is the phase diagram for the checking purposes, if the periods it's good or not good. Here is the summarization of the experiments in one table. Here you can see the left side, the detrending methods I use to find the good values, and the right side can be seen the rotation periods with filters or without filters. But we can say that the rotation period seems somewhere around 47 seconds for this object. But after the verification part, the RMS showed a deduplication of 45 number, the smallest number, which seems to me that the full rotation period of this object is actually 95 seconds, because it was a symmetric rocket. I found similar value. It was measured for this NORAD ID for this rocket stage almost 10 years ago, and measured almost the same value, 104 seconds. So comparing to the value, it suggests that the rotation of the debris has accelerated, but it's only apparent periods, so it's not sure, it's only suggested. I brought a second case study. It's a telecommunication satellite. It was released 85 from USA. I did the same process. We had two light curves and executed some days experiment, and with the two light curves can see that the frequential analysis algorithms handshaked and showed that it's 55.4 seconds, the rotation period of the object. But after the research and during the verification process, I figured out that the final value is actually the 110.8 seconds for a full rotation. It's because this Intelsat telecommunication satellite equipped with solar panels on both sides. After some case studies, not only ones that can be seen on the slides, some general conclusions that the quality of the light curve is very important. Otherwise, they can lead us very stupid rotation periods. And the filtering also very important because some data points belong to the circumstances and the environments, not the final results to the objects. And using multiply frequency analysis techniques, it's also considered because not all of the technique can analyze the different shape of the light curves. During the verification process, we can use the period folding visually. We can fold the curves to each other to see how they curves each other, and use mathematically with the Fourier function. There is still future in the analyzing of the light curves, such things. Not only the rotation period can be concluded, but we can do shape estimation from the light curves. One of the way, I've read in several publications that they try to generate synthetic light curves with different geometric properties and comparing to them to the real ones, and that way to say something to the original object in the space. If we can better understand the temporary changes in the rotational attitude, it can lead us to better re-entry predictions. From my side, thank you for the attention. Any question? 2? 1? No.
Thank you, Peter. And let me call our last speaker, who is Henrik Hargitai from Unren. And the title of his presentation is WIA-E, Prototype Planetary GIS for Research, Mission Planning and Outreach. Yes.
So, ladies and gentlemen, my talk will be not just the last today, but also I'm representing the other end of the pipeline, starting from you guys who build things, and I'm on the user side. I'm using the data that are collected by these devices. In my case, I will speak about data from Venus, planet Venus, and since there is a cloud layer on Venus, the only method to explore the surface is with radar. So the data that we are using, when I say we, I'm a planetary scientist, a planetary geologist, perhaps. So the data is coming from radar reflectivity data, radar emissivity data, and radar altimetry. So these are all pixels collected from all the surface of the maps. And my talk, the VGIS, GIS is Geographic Information System, is a collection of maps. So we call it higher order data. The raw data is radar. Then maps are made from the radar data, well, first mosaics. Then people, planetary scientists, interpret this data and tell this is a volcano, this is an impact crater. And then thematic maps are made, crater map of Venus. Then this GIS collects tens of maps, well, actually 200 maps into one system. And then if you use artificial intelligence or machine learning to sort out these thousands of data points, then you will be able to tell much reliable way what is in fact happening on the surface of Venus and what has been happening in the last 1 billion years. another problem. So I created this catalog of Venusian surface features. And I need to tell that this work started at ELTE University, well, 20 years ago. And then these catalogs is just a collection of maps. And that's not enough for a proper way to handle the Venus data. We need to turn upside down the logic of exploring Venus data from moving from a collection of catalogs to an index of places on Venus, when the basic unit is not a map or an item on a map, but the basic unit should be an item on the surface of Venus. Basically, an inventory or a census of how many features are on Venus and where these features are. I call these features places. If you have read, probably you have read The Little Prince of Exupéry. You may remember the geographer. There is an illustration in this book. The geographer sits behind a large table and receives the guests who arrive from different planets and tell him, I have a volcano on my planet, I have this on my planet. And there is a big book where this geographer writes down everything, every surface feature, where is it, and what type is it. So this index of places that we develop at Hunden is going to be this book. And you may be surprised that this kind of database is not existing right now. So it's a valid project to generate such a book. The 4 principles of this index should be that it's diverse, it represents a big diversity of different data types. Equity, which means that the data is more balanced throughout the globe than any of the maps it uses, because it combines many maps. And it includes many types of data, from scanned PDF files that were generated 30 years ago and has never been digitized, I mean, to character recognition. It's just a picture. And it will be accessible. Actually, it has been posted to Zenodo already, so it's open access. These are the layers, 200 layers in the VGIS. You can see that some types are repeated many times, like crater databases. There has been many crater databases created from Venus data in the last, the first decade of Magellan exploration. So and these are not similar, these are not identical to each other. Some scientists consider a pattern, a visual radar pattern crater. Others say it's a volcano. Others say it's nothing. This is how it looks like, and this is how it looks like online. You can visit my website, which is there, hargitai.web.elte.hu/VGIS. This is an experimental, I'm developing this tool where all the layers will be selectable. So it's a new approach actually to what a map, what is a map in a digital environment. It has many layers, and you can turn off and on each layer individually. And you can make calculations using the combined layers, and you can visualize Venus in a way that you like. So it's not the cartographer who designs the map, but it's going to be you who designs your own map from the hundreds of layers, the hundreds of options, color bars, everything. Yeah. So again, the website, and these are two screenshots from this layer. But this is called Lambert projection, two hemispheres that has been used in the 1980s, 90s. It was very popular to represent Venus, and it disappeared with online maps because all the online maps use equirectangular projection. And technology brings back this very old 18th century look of a planet. So you can, if you want, you can work in this environment. Again, this online GIS can be used for research because researchers can use the data to calculate things for their own research focus. It can be used for mission planning. Actually, this whole project is funded by the Envision mission of the European Space Agency. And it can be used for outreach. Anyone can access it. I'm not saying it can be used in education, in primary or secondary education, because not too many teachers teach about Venus's geography at high school. But perhaps at university level, some, well, it's not too realistic, yes. So you can use it for research or outreach. Kids, before they reach 12 years of age, are really interested in space. So there is a big gap until they go to the university and will be interested in space again. But so it's a multi-use system using multiple layers of sources. And please go to the website and try it out yourself. Thank you.
Thank you, Henrik. Any question, please? No? Thank you again. Thank you, Henrik. And let me ask to László Bacsárdi to wrap up the first day of our conference. László, please.
Thank you very much, Carmen, for chairing this plenary session of Science and Technology. And with this, we will conclude our program for today. I just have 3 remarks. Tomorrow, we will have a full online day. You can find the Teams link in your registration email. So I encourage everyone to join us tomorrow. We will start the conference at 9:30 local time, Central European time, with an invited talk followed by different technical talks in a section of Science and Technology. Then we will have a lunch break. After that, we will have a highlight talk and talks about education and outreach activities. The second thing that I would like to say as a closing of the first day, that we are really thankful for our media partner, Galileo Webcast, to online streaming this day, and the recording will be available on the YouTube for everyone. We published the book of abstracts, which is available on the website of the conference, and we notified the authors that we will publish full papers during the coming months. The submission deadline for the full papers is in 2 weeks from now. So I encourage everyone who presented already his or her work or will present the work tomorrow to submit their full papers. Having said that, we are almost ready to close this day. Just one last thing, that after the English session, we will have an official side event organized by the Women in Aerospace Europe. This side event will be held in Hungarian at the ground floor in the room IB 023, which is just outside of this room at the left side of the building. And we will have a roundtable discussion about analog astronaut missions with 2 Hungarian experts on it. We will start this side event in Hungarian language in 30 minutes, so 6:45. That event will be not live stream, so this is only for the in-person participants who are here with us at the university. With that, I would like to close the day and see you tomorrow at the second day of the Space Conference. Thank you very much for your attention.